Hello, I'm Colin Daly of Campbell Scientific in Logan, Utah. In this video, I will demonstrate how to implement double precision calculations in CR Basic and how to avoid common mistakes that lead to unexpected results. For most measurements, single precision is adequate for processing and reporting results. For example, it does not make sense to record 14 decimal places for a measurement from a sensor that can only achieve 2 decimal places of precision. In CR Basic, all declared variables default to single precision unless specified otherwise. However, there are some applications that require a high precision due to a great deal of mathematical processing, such as fast Fourier transforms or totalizing a measurement through time. Another application that may require double precision is the reporting of sensitive GPS coordinates. Standard GPS accuracy is 3 meters. Accuracy is lost when using single precision for decimal degrees. Double precision is also required when doing calculations with GPS coordinates to see movement. To begin, let's look at the difference between single and double precision formats. Single precision, sometimes called FP32 or float32, is a 32-bit variable that conforms to the IEEE 4-byte floating point standard. The first bit sets the sign. The next 8 bits contain the exponent value with a range of -126 to +127. The remaining 23 bits contain the mantissa or fraction. In Campbell Scientific data loggers, the IEEE 4 data type provides 4 bytes of precision with 7 digits. Double precision, also called FP64 or float64, is a 64-bit variable with twice as many bits as single precision. 64 bits conforms to the IEEE 8-byte floating point standard. The first bit sets the sign. The next 11 bits contain the exponent value with a range of -1022 to +1023. The remaining 52 bits contains the mantissa or fraction. An implicit leading bit with a value of 1 gives precision of 53 bits. In Campbell Scientific data loggers, double precision or IEEE 8 in CR Basic provides 15 digits of resolution with 14 significant digits. To achieve double precision when doing calculations in CR Basic, 2 steps are required. Declare all variables used in the calculation as type double and append all literal numeric values used in calculations with an R. If either of these steps is missed, double precision will not be used in the calculation, resulting in a single precision value. The rounding error caused by single precision might not have a significant impact on the result when the computed value is only used once. But when using that calculated value in subsequent calculations over and over, errors may accumulate, resulting in unacceptable precision. This program example shows how precision is lost when calculating a repeated mathematical formula that incorporates previous results. Notice in this example, only the double count variable is declared as double. The single count and diff count variables are single precision since they are not declared as type double. Over the course of 10,000 scans, the single count value increases to nearly 4 greater than the double count values due to the accumulated rounding errors in the single precision values. A difference this large will be unacceptable in applications that require high precision. Next, let's look in more detail at how to correctly program double precision calculations in CR Basic and how to avoid common mistakes. For double precision to be carried through a calculation, both the storage variable and other variables used in the equation must be declared as type double. In addition, any literal numbers used in the calculations must have R appended to the end of the number. This program example demonstrates how to correctly set up double precision calculations. Since the variable is declared as double and both values in the calculation have R appended, the calculated value remains as double precision and retains the full resolution of the information as expected. The next example demonstrates the most common mistake in CR Basic that results in single precision when double precision is expected. In this case, the final storage variable is declared as double, but one of the values in the equation is not appended with an R. So even though the result stored in the variable has more than 7 significant digits, the last 3 digits were rounded. If this result is totalized through time, the rounding error will become increasingly greater. In this final example, all of the literal values in the equation are appended with an R, but the final storage variable is not declared as double. In this case, only 7 digits of precision will be reported. In summary, when double precision is required, take care to avoid these mistakes by properly declaring your variables as type double and appending all the literal values used in your calculations with an R. A note of caution though, using double precision uses twice as much storage space. It also greatly increases processing time, so be sure to only use double precision when it is necessary for your application. Otherwise, you will needlessly waste storage memory and decrease processing bandwidth. Contact Campbell Scientific with any questions about when to use double precision calculations or if single precision calculations are sufficient.